So, just a quick disclaimer, we're not actually going to build our own, but we're going to show you like what happens if you're very good at browsing the internet and buying one. So, let's see. First of all, lawyers make me say this. We're here because we do cool shit in our own time. We're not representing our employers or the university or whatever. Also, what we're going to be telling you is stuff that we've been working out, while working on a project. We haven't had formal training or anything, so please double check anything we say if you actually want to use it. Well then, now we have that over with. I'm Peter Boss. I'm an offensive security researcher at the Intel Corporation, and you can find me on Twitter. Besides that, I'm a hardware hacker, which means I break all kinds of things. I like to build things too, but breaking is more fun. And I might spend a bit too much time on the various auction sites trying to buy cool lab equipment, which is kind of where this came from. Now, together with me is Peter Sawinski.
Okie doke. Oh, damn, this works. Hello, I'm Peter Sawinski. By day, I do security studies at Line University, and not the type of security studies you're probably thinking of, more of the kind with, Al-Qaeda, ISIS, and the IRA. Thoroughly good time. I'm also the person running a lot of the chemistry stuff over at RefSpace, and recently I've been getting into photographic chemistry, trying to reverse engineer some of the old Polaroid peel-apart process, and I realized, hey, a lot of these patents, papers mention electron micrographs. So that kind of got me into the project. Also, I'm a eBay addict, Marktplatz addict, eBay Kleinanzeigen addict, and basically, if it's sold on the internet, I want it in my house or office. And now we'll head back to PBX.
Right. Okay, so for me, this kind of started with looking at all these cool photographs you can find of chips on the internet. I was thinking, I want to do this for myself. So I started out just modifying crappy old biology microscope, so it does the right kind of lighting for that. And that gradually got out of hand. And at that point, I was able to do some pretty interesting stuff with it, some of which involved figuring out microcode on Intel CPUs at one point. But then, yeah, I was kind of not satisfied with the things I was able to see. It was like, okay, I can see enough to do my work, but it is still a bit fuzzy. And then I remembered what I learned at university. Yeah, optical microscopes simply don't get much better than resolving things of about 200 nanometers. You can get a bit better with some fancy tricks, but there is a fundamental limit there, the laws of physics. Yeah, so you need something else. And, well, that something else is the electron microscope. It will do 4 nanometers resolving, or even way less. The reason I have the 4 nanometers here is the one we ended up having, and that's what it does. So, but there's another cool feature to it that kind of sets it apart from the optical microscope. An optical microscope tends to look at a really thin slice of something. So only like a very small distance is in focus. As you can see here on the right, that's an optical shot where you see the bond wires kind of fade out because they're out of the plane. And on the left, you see a fly through our electron microscope. And you'll notice that it's more like a photograph. You've got a lot of like depth of focus there. It's kind of like a nice macro shot instead of being what you expect to see through a microscope in biology class. So these are two things that might really make you want you have one of these. Sorry. So we went on eBay and like, oof. You know, I too want to drive a nice car, yet I don't. So, yeah, let's keep looking for a bit. And then my friend Shiz, while browsing Japanese auction sites for arcade cabs, thinks, why don't I look here? And he finds this. Now, that's about 2,000 euros. But it's a big thing. It's in Japan. So, fortunately, he routinely imports these arcade cabs with his thing he volunteers at, so let's just throw it in one of their containers and pay a fair share of that. It'll be fine, right? So this is, by now it's March 2021. And the prices were a bit high. So we're thinking, let's wait. Surely they'll get better, right? Not exactly. So we're waiting and we're waiting because, simply at these rates, the place he volunteers at wouldn't have been able to afford that. It just didn't make business sense. So that thing was sitting, I think, in Osaka somewhere for the better part of a year. In the meantime, she just keeps looking. And I get this Discord notification. Hey, I found this. It's in Germany. Looks pretty cool, doesn't it? Only 2,500 euros. I'm like, sure, okay. Looks a bit old, but nice. And we could even pick it up by car. Or have it shipped for not too much money. So, also has some nitrogen dewars with it, a sample prep device, and another one. Gotta be a catch, right? Yeah, it's big. And not just is it big, it needs to go through there. Oh yeah, and that's also on the 1.5 floor or something. Well, in the end, we got it sorted, which involves such fun things as having a friend from the hackerspace call a German window contractor for us to rip out the window of some random business's building, which they let us do. They were like, no, you have to get the contractor. We're not going to help you. Let's see it. Do not turn transmitter off. Sorry. Oh yeah, there were no vans with tailgates available at that moment, so we had to do some load bearing club mate. Surprisingly, this is not where the next hurdle appeared. That was just a bit later when we found out that even though we literally took it out of the lab it was in ourselves, it had been playing home to some rodents. Yeah, see those stains? That's not just stains, that's piss and crap. So we were really worried, is there going to be a dead animal in there somewhere? Is it going to go up in smoke when we turn it on? So I had to take the whole thing apart, at least the electronics part of it, and put it back together. And you know what? We're very worried, but we were about to turn it on, and it works. Just works. I mean, sure, turns out we will have to do a lot of work to get it working well, but we got an image and it's all working. Now, that's a bit of the story part. You might be wondering, how the hell does such a thing work? Is it all very complicated? Right? It's not just a bunch of lenses and you stick a slide under there. So, yeah, let's take a look. First of all, especially the more insane kind of STEMs you find in universities have a lot of bells and whistles on the actual physics part of it. And there's also always a lot of knobs. Now, that is not specifically the one we have. The control panel you see there is. So you might be wondering, how does that work? Where can I even start to understand this, right? Well, I hope everyone here is old enough to have been in front of one of these. Well, maybe not a terminal, but a television or a computer screen that works like this. It's really not too different. If you have a picture tube, like as in that screen, you have something that emits electrons, something to accelerate them towards the anode, a bunch of lenses made out of either electrodes or coils, and some coils to deflect the beam with, so to move it around. So that's something I hope most of us have kind of a bit of a feeling for, at least conceptually. Now, it turns out the electron microscope is not that different. We have what is called the column instead of the neck off the back of the screen, and it's got the gun, it's got the electron beam coming out of that, a bunch of electromagnets working as lenses, some apertures to make sure the beam is nice and clean, and some coils to move the beam around. Instead of hitting it at a screen, we're now focusing the beam on something we want to view. Now, you might have noticed something about the name of the device. It's a scanning electron microscope. So what's the scanning part mean? Well, just the same as it does for a TV. Instead of forming an entire image at once, we're moving a dot around, and yeah, in doing that, we can kind of just have a signal against time, just a video signal, and plot that. Kind of like having a scope with an X, Y, and Z input. Now, what's the signal we're plotting then? How do you get an image out of slamming electrons into a sample? Well, it turns out there's a whole lot of physics that happens. You have electrons coming out, you have electrons reflecting, X-rays, normal light coming out, there's some electrons going through, there's a current flowing out of the sample. Each one of these you could record and plot against position, and you'd have an image. And in fact, for about each one of these, there is a module you can get on a SEM that will do just that. We're going more into that later. So what about those controls, right? Do I need to know all this? Do I need to understand this physics to use one of these? No. Really, the controls aren't that exciting. There's a few for setting how fast those electrons are going by deciding how many volts you want to put on the anode. And you can turn it on and off. And you can monitor how much current is actually running there in your beam. There is the video mode. How many lines, what's the frame rate? Also not terribly complicated. And I'm sure everyone will have a sense of what these do. And yeah, that up button, that's the closest thing you're going to get to the CSI enhance thing in real life. Because you're not zooming in on a digital picture, you're actually changing the area that you're focusing on. So like, if you push up, you will see the images blow up, and it will stay sharp and in focus if you've done everything right. So it's really cool to see. And of course, you've got to focus it. The right-hand one here is the part where it gets annoying. You need to make sure that your beam is round. It's not too much science behind operating these. You just fiddle with the right three knobs until your image is good, and it can be very frustrating. Fortunately, there's a nice auto button there. If your SEM is new enough, it might actually do something. So I've kind of been avoiding the elephant in the room here. It's just like a picture tube, right? What's the one big difference besides what we're aiming these electrons at? That tube gets sealed in the factory. It's at vacuum. It's just that way. You buy it that way. It's fine. Here you want to be able to put stuff in, so you can't do that. So yeah, you gotta get all the air out of that. And you might be wondering, get the air out of that. Engineering doesn't do absolutes. All the air, no atoms left? Nah, not how it works. So instead we look at how far a particle could travel without bumping into a molecule of air. That's what we call the mean free path. We need that to be at least a bit longer than our device, otherwise the electrons will just hit some air molecule, go off in a random direction or get absorbed, cause problems. Well, normal air is at 1 bar, and it's about 66 nanometers is what you can travel without bumping into a molecule. So if you start having a vacuum, like maybe a vacuum cleaner, that doesn't do very much. Now, if you go to your hardware store, buy a vacuum pump, okay, we're getting somewhere. Still not quite there. Okay, what if we go professional? What if we get like a real vacuum pump, right? Scientific grade thing. Okay, getting somewhere, but that electron microscope, that's about yay big. You need more than 10 centimeters. Now there's a problem here. If you want to pump the air out of something, you're kind of relying on air behaving like we're used to with gases. Like you pull out a piston and the pressure in it decreases, right, if it's sealed? Well, it turns out if you get to really low pressures, air kind of behaves more like a bunch of like ping pong balls bouncing around instead of like a continuous gas. So you need a different kind of pump. A normal pump won't cut it anymore. So that's where these come in. The so-called diffusion and turbomolecular pump. And they go to insanely low pressures. That's in millibars, by the way. So we're talking like a lot of zeros, even after, like if you're doing it at percent of something, like that's very, very low pressures. Now, these are not things you commonly deal with. So I'm kind of going to show you the main differences between these, because this is actually important, as older SEMs will have mostly diffusion pumps. Newer SEMs will have mostly turbomolecular pumps. And it's not just as simple as the turbomolecular pump is newer, does better. No. These are nice, they have no moving parts. They do some magic with oil, and thus not having any moving parts, they don't really break. But the oil in there is very special and expensive. Think a fill of oil might be 500 to 1,000 euros. And if they fill your whole SEM with boiling, maybe even burning oil. And that is a terrible work to clean up. Also, they take a while to warm up, like half an hour or something. So you decide, oh, I want to look at something. So you turn the power on, you sit there for half an hour, and okay, light comes on, I can use it. Then you can change your sample quickly, provided there are enough valves in the system. But and then at some point you're like, oh crap, I need to catch the last bus out of the hackerspace. Let's turn it off. Nope, can't do that. You have to stay around and wait until it's cooled down, because the water pump cooling it still needs to be running. So yeah, they're not ideal, but they also really can't break that easily. Now, turbomolecular pumps are cool. They start quickly. They won't send oil everywhere. And they're doing around 90k RPM. I think that's more than a jet engine. And the way it works is the blades are moving faster than the molecules are at average, and it just smacks them out of the way. Now, these can be expensive to fix. There are some bearings in them. If those break, the whole thing will kind of just die if you're not replacing them in time. And it's not really something you can easily fix. If you don't maintain it, it will just break, game over. I'm thinking, how bad can it be? I mean, people say things is like beyond repair all the time. How bad can it really be? That bad. There's a lot of kinetic energy in that rotor at 90,000 RPM. If something seizes, it will just tear itself to shreds. And there's no coming back from that. Now, that was kind of the basic stuff. We're already kind of a bit into technology, but there's some more technology differences you need to know if you're thinking about getting one of these electron microscopes or using one. Besides a vacuum system, we need to get the electrons from somewhere. And what the display tube does is it just has pretty much a light bulb. And that light bulb, because it's hot, the electrons will also statistically sometimes be outside of the metal. And if you put an electric field on that, they'll just get ripped away and you have your beam. Just like the old radio tubes you might have in your guitar amp. It works. That's good, because these are cheap and they don't require that much of a vacuum. They're also not too bright in terms of the image that you get out of them. They're fine for low magnification. Once you get really high magnification, you want to be so selective in the electrons that you're using, because you want a really small beam, that with this, you're kind of fighting the signal-to-noise ratio. Now there's other options. You can place a fancy crystal on top of it that is better at emitting electrons. Great, but these are expensive and they also need a better vacuum. I think that's not a large difference, but we're getting into the domain where it's not just a matter of hooking up a pump anymore. No, if we're getting into the domain where fingerprints or a sample that's not completely dry will just mess it up. So that's a bit annoying. Then there's field emission, where you just rip the electrons out of the material directly. It's great, it's amazing, but it also needs insane vacuums. You can't use O-rings anymore. You need to use metal-to-metal seals. A fingerprint somewhere will mean it won't work, might even damage itself. They're more expensive than you're probably willing to spend on a microscope in the first place. So, in my opinion, it's the tungsten filament that you want to go with, because that's the one that you can realistically, as someone without a lot of experience, keep working and replace. You might even be able to put your own tungsten wire on one of the bases if it breaks and you don't want to buy a new one if you have a spot welder. So, about all those signals. Each one of these is something interesting. If you want to know about the surface of your sample, you might want to look at the things that start near the top. If you want to know more about the actual composition, there's things like the X-rays or backscattered electrons that can tell you something. And your sample might even emit light when you hit it. Like think of a phosphor on a CRT. That'll glow if you hit it with electrons. Well, it turns out a lot of materials actually do, and you can measure that, and that's one of the things you can use. Now, the way you actually put this into practice is there's detectors on your SEM. So you have the main column, which serves to get the electron beam onto your sample, and then you have detectors you stick on to measure these signals. The most common one you'll find on every SEM is the secondary electron detector. It's also sometimes called the Everhard-Thornley detector after its inventors. And it's pretty much just a standard. Every electron microscope will have this. And what it does, it looks at the electrons that get emitted when you hit your sample with electrons. So imagine kicking a ball into like dry beach sand. Some sand will be thrown into the air, right? Like same thing as with the sea of electrons in matter. You shoot an electron in there at high velocity, you get a few slow electrons out. This will pull those electrons towards it and then convert it into light. You see little flashes, it measures that, and you get really nice images, such as this one. Or these. So it's pretty cool. You can also go to pretty small scales there. There's little white specks you see there on the right. That's actually vias between different layers in a chip. There are, well, 200 nanometers across, I think. So you could get pretty high resolution there. Now, sometimes you want something else. With this, you only see the top surface of something. If you're looking at a chip and you didn't etch it right to the exact layer where you want it, you might want to look a little deeper, right? With an optical microscope, you're always looking through the transparent parts. With an electron microscope, in secondary electron mode, you're only looking at really the top bit of it. So there's also the backscattered electron detector. That's a lot more useful if you want to look a bit further inside the sample, because it looks at the electrons that got turned around. So you have your high energy electron, there's an atom there, it slingshots around and it comes back to one of these photodiodes. And the signal is also more dependent on what's in there. A higher atomic number, so like heavy metals will reflect more. So you get images like this. I don't have the detector yet, so this is from Wikipedia, but you can see like there's some spot here of some heavy metals in this glass, and the rest is just silica. And heavy metals really stand out as being these bright spots. So this can be useful if you're looking at a chip that isn't perfectly prepared. Now there's even more precise things you can do in terms of composition. This just tells you, oh, that bright spot probably has a higher atomic number. You can also look at the X-rays. And the X-rays actually have a spectrum that depends on the actual element. Just like when you have a neon sign, you can know what gases are in there by looking at the spectral lines. We can do that for X-rays in this case as well. Downside is most older detectors for this require liquid nitrogen, and that's a bit of a hassle, but it's really cool. Like we have one of these, and you can put something on there and know what it's made of. Like, what is that white ceramic? Well, it turns out it's like some sort of magnesium silica oxide mix. Oxygen isn't really there because it's a very light element. It's not good at emitting X-rays. Now it's even better. This is one signal, it's 1 point. But what if we do this for a whole lot of points, right? Just like we were doing with the scanning earlier. We actually can make a map of what element is where. Or like in this chip, where you can see the soldering and the bond wires and the chip itself, all different colors. This is not, well, it is false color, but it's not made up by some artist. This is actually different signals from different wavelengths of X-rays that we're looking at. So yeah, that's a kind of, in my opinion, a really surprising ability to have, because you can actually look at the composition and see it mapped out like that. So yeah, this is kind of the basic technology that we have here. And here is where my colleague takes over.
So, can I have a microphone, please? Thank you. So now that we have all of our theoretical and practical background, how do we actually capture these images? Well, turns out you can just grab them like any other analog or digital video signal with a frame grabber. However, as it turns out, that is not always the best way to do it. It can introduce noise and cause other problems you can get around by using something called a photo CRT. Because two CRTs are always better than one. Basically, what you have is a CRT built into the chassis of your microscope, and then you take this delightful device, which is a 4x5-inch film camera. Remember film? And stick it on top. Unfortunately, you have to like figure out the exposure, but when you do it once, it'll just stay that way. And the best thing is, you can load it with Polaroid film, so you don't even have to go to the 1-hour photo place. Unfortunately, that film has been discontinued, and this might be part of why I want to reverse engineer it. You also have something called a chamber camera. Now, this is really, really important because it's actually kind of like a webcam inside your vacuum chamber. Why is it so important? For certain types of things, you want your detectors really close to the sample. And I hear you asking, how do I not crash my $40,000 detector into my €2 sample? Chamber camera. We have one, and if you come on down and see the SEM later, we can show you how that works. You also have new versus old electronics, or well, new versus old SEMs. Old SEMs are a thing you'll have to be prepared to put love into. They'll be crusty. There's a lot of electrolytic capacitors. However, documentation is great. For our Hitachi, we have component level schematics, like all of them. And we know what the components are. They're commercially available. If we really wanted to, we could duplicate the thing. However, new SEMs tend to get more complex. You have a lot of ASICs, FPGAs, and if you need a new one, they tend to start around $900 on eBay, and that's assuming you can find the right component from a place that services SEMs. A lot of modern manufacturers aren't exactly going to send you a replacement board because, come on, just get a service contract. It's like $5,000 a year. Okay, oh, sorry. So stages are another thing we need to discuss. Right here in the back, you see a manual stage with knobs, like the 70s. And here you see the stage of the microscope that we actually brought here because we're very smart and camping with an electron microscope is a good thing to do. So mechanical ones use micrometer screws, which is tedious. I have unironically had to twist something around 40 times once to get it into the position where it will not crash if I try to open the door. Motorized ones have joysticks, which is great, but more importantly, you can do automation, which saves you a lot of time. And then there's something called a eccentric stage, which kind of follows the more axes, more better rule, and will be very complex to take apart. Actually, for all of these, please consult your manual before taking them apart, because a lot of them have very factory calibrated linkages. So now let's discuss the actual practicalities, your physical requirements. So you decide to go on some government auction site and you win one. What do? What do you need? First of all, you're going to need a water chiller. You're also going to need a roughing vacuum pump. Those are often included. And you'll definitely want to get an oil mist filter, because good God, when you first rough it down, you don't want your pump to start vaping oil mist all over your nice new equipment. And then you might also just want to run a plastic tube outside. That's what we currently do, and it's not failed us yet. Vibrations are a concern, and initially we were much more concerned about them, but it really comes down to your model and whether it has vibration dampening. External fields, an important one. If you have a collection of neodymium magnets, please keep it far away from your column. And also very important, this was actually like an exclamation point in bold in the Hitachi manual, make sure your floor can bear the weight. Grounding is another thing every manual will tell you to consider, and that is actually the PC running our EDAX or EDS. Look at that copper. That is thick. The whole cable weighs like 2 kilos. And last but not least, if you're running an EDS, you'll need liquid nitrogen and a liquid nitrogen dewar. We have a liquid nitrogen dewar. It will not fit into our car. So, once again, RTFM, get a manual, figure out what you need, and make sure you can hit that. There are some risks of running a SEM. First of all, you have a vacuum chamber with an electron beam. More specifically, the electron beam is also crashing into something. So, kind of like an X-ray tube, except it is an X-ray tube. So if you actually have a commercial off-the-shelf or used SEM, and you've not modified it in any way, and it's not been modified, and all of the blanking ports are covered with their original parts, you're A-okay. However, when you start bolting stuff on, you have to start getting careful about making sure that your metal is thick enough to stop all that delightful radiation trying to leak out. Also, it does need to be said that SEMs are lab equipment. There is a chance of contamination. And it is generally a very good idea to clean them extremely well and rub down every surface while wearing gloves, an apron, lab coat, and safety goggles. Now, because that wasn't fun enough, we also have some legal stuff. For example, in the Netherlands, if you're going about 30 kilovolts in a vacuum chamber, you will need to register that with the safety authority. Check this for your country if you're going to be buying one, or don't, your choice. Also, make sure your SEM isn't blocking a fire escape route, because they are big.
And yeah, we're hello? No. Yeah, we're not lawyers, by the way. You might want to check this, but yeah.
So, software is another fun can of worms. If it's newer and you get a PC with it, there's a decent chance you'll have the software. There's also an equally decent chance that the seller removed the hard drive and drilled a few holes through it. The good news is, electron microscopes tend to come from a few manufacturers, and what you do is you Google the model number and you figure out who else owns that model, and then you send them a nice email saying, hey, I noticed your lab has the same model of electron microscope. Any chance you could send me a copy of that CD, pretty please? I promise I won't tell anyone. There is also the problem of calibration data, but if you get calibration slides, which are pricey, you can generate your own, and your manual should provide all the procedures for that. Battery-backed RAM is another thing you can be concerned about. Ours, I believe, had a coin cell on it. So that's also another thing to check when you're disassembling and initially cleaning your new microscope. Now, consumables are always a thing. So for your detectors, you have scintillators. See these two little discs? When we first bought it and took it apart, it was the one that you see on the top. You will notice it is clear, like a piece of glass, which is bad because it's supposed to be coated in opaque scintillator. So after going on eBay and thankfully finding the exact part for $100 US, we replaced it and our image quality went up exponentially. And we no longer had to kill our machine by running it at full power. Next up, if you're doing EDS, you need liquid nitrogen. And if you have a mishap in transport, you'll need a new photo multiplier tube. But the good news is those are pretty affordable compared to all of the other stuff that can go wrong. Your vacuum system will need maintenance. If you're running a turbo pump, you'll probably have to get a little oil cartridge. And here's the thing. I'm a big fan of buying new old stock. Not a thing to buy new old stock. The good news is they're still made for almost all pumps, but prepare to spend around $70 to $150. O-rings are important, and if you're running diffusion fluid is important. And that oily fluid is not cheap. Filaments you'll have to buy, unfortunately, especially if you're running tungsten, which most hacker SEMs are. They last around 10 hours each, but...
Wow. That was mostly when we weren't quite good about calibrating it yet. When you get better, they should be able to do a few hundred, but it's, yeah. Expect to go through the first few very quick.
And the more important thing on those is, especially if you're working with small budgets, they tend to come in packs of 10. So $50 doesn't sound bad, but when your supplier says, yeah, MOQ is 10, that is something you might have to save up for. Apertures are another thing you might have to replace, and you can get them custom made, or there are a lot of new old stock ones. You can also bake them out in a vacuum chamber and make them last longer. And last but not least, one we recently discovered was something that could go wrong, are vibration dampeners. Basically, the rubber in ours kind of deflated over the decades, and after adding a few nuts and bolts, we raised it up, and now we can play Dance Dance Revolution next to the SEM. So, transport. Remember how your washing machine comes with all those bolts in it that you have to remove? Well, the same goes for your SEM. More importantly, you have to put the bolts in before moving it around. Otherwise, you risk damaging a lot of stuff. Detectors. See the thing covered in a glove. Do that. The last thing you want to do is accidentally put a ton of weight on that and not support it. And care really is of the essence. So that over there is the photo CRT port, and we put a glove over it to stop whatever stuff might be in that van from getting in.
Yeah. When saying don't put a lot of weight on it, that big liquid nitrogen tank, yeah, if that's gonna like wobble around transport, it will bend shit. You don't want that.
Yeah, that would be bad. Very bad. Okay, sample preparation. Now, for this one, I have brought some visual aids. So this is called a sample stub, and it's basically what you mount your sample to. If it's conductive, you can mount it straight away using one of these nifty double-sided carbon tabs. They are cheap, and the cost is basically negligible. And here's one I made earlier. Very simple. Problems start happening when you have non-conductive samples. Basically, you need a path for the electrons to take. And you'll have to do something. The easiest way is gold sputtering. And that basically means you buy a sputter coater, as pictured. It's a very cool instrument. Look at that plasma. But it is pricey, and it is gold. However, the cost of the gold on the actual sample is negligible.
And sometimes when you buy one, you literally get about 3 times what you paid for it in weight of gold still in it, because the seller probably didn't know it was upgraded with a bit more gold than should have been put in there.
This message is brought to you by eBay Kleinanzeigen.de. Now, stuff gets even funkier if you want to do some more EDAX, EDS stuff and map samples that aren't conductive. What do? How do I get better results? You evaporate carbon onto it using a carbon coater. And then you get something clear to X-rays, so you can still detect the X-rays. However, not the best choice if you want to image stuff visually. Documentation. Oh, documentation. This is all stuff that came with our Hitachi Sen, and it has saved us so many times. First of all, RTFM, please read the fucking manual. It would have saved us a lot of pain to have taken maybe 6 hours to read every single page of the manual twice. But you know, you just buy the thing and you're excited and having a good time, and before you know it, you wonder what fucked up. Well, the manual explained it to us. If you don't have a manual, which is something that might very realistically happen, go to MicroWiki. They have a lot of manuals. Also, do what I mentioned earlier, Google for the SEM model, figure out if some university is still running one, email them. Maybe they have a PDF. Another thing you can try and will be very helpful is just find a manual for another SEM made by the same manufacturer in the same range. Because a lot of the stuff is very basic and applies to a lot of their instruments and is still definitely good to know, like warnings.
Yep. So now you're thinking, all that effort just to take some pictures. I mean, it's a good time, looking at things up close and seeing how beautiful they really are, but sometimes you want to do more, and sometimes all that stuff about reading manuals, we're hackers, right? We got to do more than what's in the manuals, more than was intended. So one of the things you can do, besides look at things, is actually modify things with it. Like, not a chip, you need a bit more expensive equipment for that, unfortunately, but say you have plastic, and you shoot it with electrons, it might, like the chain will break and you could do things now. So there's this thing called E-beam lithography, which is you take a sample, stick it on a PC fan or something, cover it in a layer, like put a drop in there, it spins around, it's covered now in a layer of plastic. And then you can draw things on the plastic like an Etch-a-Sketch, but with electrons. Because it turns out you can put an X and Y input on a SEM, just like an oscilloscope. Let's see, does this work? Yeah. Did I say just like an oscilloscope? Don't we all love oscilloscope clocks? One second. Yeah. Okay. Sorry, this video player is being annoying. But yeah, don't you just love oscilloscope clocks? What if we take the beam of the electron microscope? The actual sample is like somewhere in here, but you can make it move around in fun patterns, even though you can't turn it off. Like if you move it faster here than in some other places, you can actually draw pictures. Now you're thinking, what's the use of that, right? What does it matter if I do like shoot some plastic molecules apart? Well, turns out that those shot apart molecules, if you use something as simple as plexiglass, PMMA, they become soluble in alcohol. So if you then rinse it with some rubbing alcohol, there won't be any plastic anymore where you hit it. If you then do that on top of something that you can etch, just like doing a circuit board, but smaller. That QR code, that's under a millimeter across, and this is really kind of a coarse one. I must say I got some interesting responses when I posted this on Twitter when people were scanning it, but like what do you put in a QR code, right, when you tweet it? It's a Rickroll, of course it is. I'm not gonna do that to you, so don't try. Yeah, the lines in there's a bit fuzzy because this is an optical image. Those are the narrowest lines in there that we've been able to make were about 3 micron across. So this is kind of cool, right? We can now make very small things. That's another thing with these electron microscopes. We saw a lot of people in other countries doing really cool stuff with them and with other advanced technology. And we're thinking, why is no one in the Netherlands doing this in our hacker community? We want more people to do that. But also, we want to start working on even more high-tech hacking, such as maybe making our own chips. There's some folks in the States that have done it. Like that's some guys work in his garage, those chips in there. Can we do that here? Like, are there people who feel like, you know, that would be cool to try? Well, we're kind of carefully looking into what that takes. This whole e-beam litho kind of appendix to this talk was what that was about. If you feel like that's cool, please come talk to us after the talk. Now, there are some useful sources you might want to look at. The Jail company has a very, very useful and short booklet, like really not that thick. It explains a lot of these concepts in somewhat more depth, definitely enough if you want to use it. If you want to repair a SEM, you might need a little more knowledge. And there's also like Ben Krasno, Applied Sciences DIY SEM. He has a lot of videos where he really goes into detail about how some of the things work. And last but not least, we're crazy enough to take the other SEM, because we have 2, right? We have the one from Japan and the one we bought from Germany. We have that one here on site. It's working. It got a bit rained on. Didn't die, fortunately. Had to take it apart, rinse it in alcohol, put it back together. Which is also why this was a bit less prepared than I hoped. But it still works. You can come try it. And yeah, that's in the arcade hacking slash... I keep forgetting the very long name my friends picked for it.
It's apparently a reference to something arcade people would know. But yeah, no, come on down. You can look at the book and you can experience what it's actually like to use. And good God, transporting all those bottles of vacuum pump oil on the shuttle made some people give me some weird looks.
Yep. So I hope you enjoyed it. And I don't, like, let's see, do we have time for questions?
We'll turn it over to our...
You have about 2 minutes, so 1 or maximum 2 really quick questions if anyone wants to. Do we have? Okay.
Comments, questions, concerns, complaints?
Then?
Rotten tomatoes?
You mentioned that conductive and non-conductive samples have to be treated differently. Semiconductors are famously semiconductive. How do you need to treat them?
You don't really coat them usually, but they can be problematic in that the electrons don't always have a path to run to ground. So if you put a chip in there, charge might build up, it might die because of that. Like you're putting it full of electric charge, right? This means that you get some imaging artifacts, because if there's a lot of charge at one point, the beam will bounce off it and it won't take the path you think it's taking. So yes, as always, there's a lot of nuance to it.
However, for example, on the SEM that we have right here, there is a convenient discharge button. So there are a lot of things you can do about this once you realize that, oh, my sample is a semiconductor, it might build charge, I need to press this button. I'm shilling for the manual now, but I hope that answered your question.
And time is up, I'm sorry. But you can probably ask them afterwards. I'm sure they will be available. So please give them a round of applause.
Thank you.